A spaceship orbits the Earth on a circular orbit with 7.8 kilometers per second. Determine the delta V required to bring the spaceship to a trajectory straight into the Sun. This is a classic orbital mechanics problem which we want to solve now. So we have the Earth here, and let me denote the mass of the Earth by me, and we have a circular orbit of a spaceship of mass m and velocity vs. Vs is 7.8 kilometers per second. The radius I denote by rs. And now we want to add some delta v to this orbital velocity so that the spaceship can fall into the Sun. So we have the Sun, and we have the circular orbit of the Earth around the Sun, and the Earth moves with velocity ve equals 29.8 kilometers per second. And now we have to make sure that when the spaceship leaves the gravitational field of the Earth, it leaves in opposite direction with the same magnitude of the velocity, so that the velocity of the Earth gets compensated. And this makes the spacecraft fall straight into the Sun. And now, in order to compute delta V, we use energy conservation, and more precisely energy conservation in the geocentric system. So energy conservation. So we have kinetic energy initially plus potential energy initially equals kinetic energy 1 plus potential energy 1. So before and afterwards. And before, it has kinetic energy 1/2 mass times the velocity s, and now we want to give it an additional delta v so that it can leave the gravitational field of the Earth. And the gravitational potential is g m of the Earth times mass of the spaceship divided by the radius of the orbit. Now the kinetic energy shall be just v 1/2 times mass times ve squared, because we need to have the velocity of the Earth in the opposite direction. And we have zero potential energy because we just left the gravitational field of the Earth. Okay, and now we have to solve for delta v. So first we multiply by 2 divided by m, so we get vs plus delta v all squared minus 2 times gme divided by rs equals ve squared. And hopefully you recognize this term as vs squared, which is a standard result for circular orbits. And now we can bring 2vs squared to the other side, get vs plus delta v squared equals ve squared plus 2vs squared. And now we can take the square root and then subtract minus vs, so we arrive at delta v equals square root of ve squared plus 2vs squared minus vs. That's the final formula. Now we can insert the numbers given in the problem, and then we arrive at about 24 kilometers per second, and that's the answer.